Hello, my name is Evan Cleveland, and this is the final Physics 2 lab, magnetic braking with Faraday's Law. The purpose of the lab is basically to collect data on a magnet that's falling through an aluminum tube to observe Faraday's Law. So obviously Faraday's Law is going to be important, also Lenz's Law, the Biot-Savart Law, and then standard Newton's second and third laws. Quick results, the experimental time was an average of 1.25 seconds. Using Glowscript, we computed about an expected 1.18 seconds, 19. So we are going to represent the magnet's behavior with a dipole model because it is essentially a magnetic dipole in real life. The only big assumption is essentially that there is no air resistance. There's no unexpected force. So system is the magnet and the aluminum tube, and the surroundings are going to be everything else. There are no really relevant initial conditions other than initial velocity equals 0, I guess. So basically in this lab, we mark the north end of the magnet, and then we're going to put a stopwatch in the background of our camera frame, then press record, drop the magnet through the tube 5 times, and then collect all that data from the videos. Excuse me. So this is the table of data, and here are the measurements from the tube, and also you see at the bottom we used our mu value calculated in lab 3. We'll talk about that later. And then the average time that was calculated was 1.25 seconds based on the data in the table. Why can't we use a ferrous tube? Basically, a ferrous tube, like a steel pipe, contains iron, which has magnetic properties. So we wouldn't get the falling action. What would probably happen is the magnet would just stick to the pipe. What happens to the magnet? Basically, the magnet's falling slower than it would in free fall because the induced current from the tube provides an upward force. Excuse me. The induced current is going to provide an upward force, which slows it down. Here's our Glowscript code. We're going to run through it really quick. Basically, just defining some physical constants, and then starting the graph in the second chunk of code. Then we create the aluminum tube object, and then continue with creating the bar magnet object. In the top right corner, you see setting the velocity equal to 0 at the beginning and time equal to 0. And then we're just going to define our B field function and the flux function down in the bottom left. And then in the top left, you see the loop that runs, that actually causes the animation. And in the bottom right, we just see essentially updating the velocity of the magnet based on the forces that are present. That's an extension of the previous slide, and then plotting the position or the velocity on the graph, and then our final run statements. So on the left here, we see the original, what we calculated in lab 3 if you use the mu value of 2.21. This is not exactly what we expected, and talking to other people, their mu values were closer to 4.5. So using that value, we get what is on our right, which gives us the time of 1.118, which is closer to what we expect and closer to what we saw in real life. Here is the Glowscript model. The red is the north end of the magnet, the blue is going to be the south end, and as we know in the model, the colors would move down. So the questions. Which color corresponds to clockwise as viewed above, and which is counterclockwise? The red is going to be counterclockwise, the blue is clockwise, and that's just using Lenz's law and the right-hand rule. What happens to the dynamics of the system when you flip the magnet around? Nothing. It would behave the same. The direction of the current is just going to change. Excuse me. For the third question, the times are actually pretty accurate when we use a valid mu value. If we wanted it to be more accurate, the biggest thing we'd do is probably make more rings of current. And then the last one, what does the shape of the velocity versus time plot tell you? The forces are going to start unbalanced as we see the velocity is changing. Then they're balanced when the velocity is constant, and unbalanced once again at the end. And finally, there aren't really any discrepancies in the model. The only sources of error are kind of from the shutter-rated camera or any errors in mu value calculation in lab 3. What if the resistivity was reduced to as close as possible to 0? the induced current would be much greater and magnetic force would be much greater, which would slow the magnet a lot, maybe even to a stop. And then if holes or slots were cut into the tube, the induced current would be disrupted by the holes, which would overall reduce the magnetic force, so the magnet would fall faster. And here are some final conclusions. Essentially, the lab very well demonstrates the real-life applications of Faraday's law and the principles that we're learning.